think most of us in the room just assumed that it didn't change anything because we haven't dealt with.
It didn't change anything.
Okay.
It was not necessary to solve any of those questions. So, yep. Yep. Determine the electric field in the spaces above and below the slab. So, a parallel plate capacitor. When you add the copper, of course, we talked a little bit about what this does, is it divided up the capacitor into two capacitors in series by adding a place in the middle where the electric field was 0. With part C, though, we're talking about the electric field between the plates. Well, we know the electric field inside the copper is 0, but there's clearly electric field above and below the plates. In order to determine the size of that electric field, there's a couple ways to do it. One of them, and I hope this is what you guys were doing, is to consider that next to the plate's charged. So again, if you don't understand what I'm saying, this is a typical dielectric problem in which the dielectric is being added to the capacitor after the system is charged. In this version, the potential difference stays a part of the system. So you close the switch, leave the switch closed, Potential difference is part of the system. When you push the dielectric in, you have access to a potential difference, which means the potential difference is going to be maintained here to here. I want to know what happens to the energy in the system as you insert the dielectric. That question, because there's obviously a question there, but you don't know how to ask it. So Boyd asked, do we need the dimensions of the block, how big it is? And I was wondering if I'd get that question or not. So I didn't know whether the stuff that we had done had answered that or not. Parallel plate capacitors. Right, that's all we have to go on. And no matter whether it's parallel plate capacitors or not, you'll notice that every place we've had a capacitance, we've had epsilon naught in the numerator of the fraction that describes the size of the capacitance. So whether it was spherical or cylindrical or parallel plate, they were always multiplied by epsilon naught. Everybody good so far? Well, our new capacitor is A epsilon over D. That's our new capacitor because it has a different dielectric. But the dielectric constant is 2, which means epsilon equals kappa times epsilon naught, or 2 times epsilon naught. So effectively, the dielectric constant determines how the capacitance will change. All right, if I look at this now, my new capacitance is 2 times A epsilon naught over D, which is 2 times the old capacitance. So when I put a dielectric of 2 inside the capacitor, I doubled its capacitance. Does everyone understand? Lawrence, you good? Yeah. All right. So putting this capacitor in there, putting the dielectric in there, whatever the dielectric constant is, it determines how much the capacitance is going to change. And it's an integer value in this case. It's a unitless value. So whatever the value is for kappa, you just multiply that times whatever the capacitance is, and you have the new capacitance. So in our original circuit, did you all figure out that the total capacitance was 1 microfarad of capacitance? So to figure out the charge is 1/2 CV squared. So 1/2 times 1 microfarad times 10 squared, right? So 50 microcoulombs. 50 microjoules. So that's what we have here. 1/2 times 1 microfarad times 10 squared, which gave us 50 microjoules. So put the dielectric in there. That one goes from 2 to 4. So you have a choice on how you do things now. I think probably the best way to do this would just be to figure out what the new capacitance of the system is. So this is all in my way, so let's get rid of it. New capacitance of the system is going to be based on the sum of the inverses. Common denominators, so 2/4 or 3/4. So my new capacitance is 4/3. One half 4/3 microfarads times 10 squared. Um, 4/3 is 1 1/3. 10 squared is still 100. Half 10 squared is 50. 50 times 1 1/3. Somebody give me a value. It's clearly going to be greater than 50, though. So 66 or 67 microjoules. Oops, not farads. Microjoules. So the new energy in the system, the old energy in the system. Now, this might not be something you're thinking about, but this means that 16 microjoules of work had to be done to put this dielectric into the capacitor. So bear with me. that means a force was required to do this. The work in the system increased. You have to do physical work on the dielectric to get it into the place between the plates. It won't go in there on its own, because the only way to change the energy of a system is to do work on the system. Now, I know that this is a mechanics, kind of concept, but you'll have to stop checking your mechanics at the door. Electrical systems store energy just like mechanical systems do. If you want to increase the energy of the system, you have to do positive work on the system. Interestingly enough, this also pulled charge out of the battery, because we're now storing more charge. We have to be. Q equals CV. C went up. So another follow-up question, step 4, how much more charge is in the system now than there was before? Capacitors are in series, so the charge went up on both capacitors. Has to, because they're in series. This isn't always what happens, though. It is possible for the energy of a system to go down when a dielectric is placed in the system. That means negative work is being done on the system. Do you understand what that would mean? Try it. Here's what I want you to try. Let's try another arrangement. We connected the potential difference, determine how much energy is in the system, but then before step 2, we opened the switch. So we charged the capacitors, then removed the circuit, the potential difference from the circuit. What would happen now? I've given you all the rules that you would need to figure this out. The answer is not easy. It's not terrible either. There are 3 possible things that could change for each capacitor. I'm not saying any of them change. I'm not saying that none of them change. I'm saying, which things do you think change when you insert the dielectric between the capacitor plates now that the potential difference is gone? You have some rules that help govern this, but I would argue that whatever's down here might not be as helpful. Can the charge change? The charge can't change. There's no place for the charge to go. The charge has to stay attached, and we know the charge on each capacitor, and we know they have to be the same. But because there's no pathway for charge on the top plate and the bottom plate to change, the charge on the middle plates can't change either. So the charge on the capacitor stays the same. Does the capacitance of the bottom capacitor change? Has to. Has to. We've changed the dielectric. Has the voltage on either capacitor changed? Yes. In the case of this system, the charge on the capacitor stays the same. The capacitance increases, so the voltage on the capacitor decreases. Which is a little weird. Now, the real question is, does that increase the total energy or decrease the total energy? So some people are either asking questions or have the answer. So who is trying to ask a question? Go ahead.
Can you repeat one more time why the charge has changed?
there's no place for the charge to go. Because I've opened up the switch, this side and this side are now isolated. There can be no flow of charge between them. I can't have an uneven amount of charge on either of these plates. So it's not like putting a dielectric in there is going to cause charges to go this way. There's no place for them to go. So the charge on the capacitors has to remain fixed. All I'm doing now is I'm changing what's happening to the plates or to the space between the plates. But I can't move charges because I've taken this path away. All right, so Gabby, what were you going to say?
The voltage, like for total voltage, would it have to go up since you would square it when you're referring to your first, like when you insert the dielectric and you're looking at it voltage-wise, the square voltage to the beginning, then compared to the other one, it's just regular voltage?
Well, we would all agree that the capacitance of the second capacitor doubled, which means the voltage has to be cut in half. But 1/2 CV squared suggests that the part that was cut in half counts more than the part that was doubled. Exactly. So the voltage is cut in half. Right? Now, I'm sorry, so the energy is cut in half because the one capacitance doubled, but the voltage across that capacitance is cut in half. We square the half, so we're going to get half the amount of energy. But, go ahead. Well, let's see. Let me make sure my math is right. How should we do this? We know that the capacitance is doubled because the dielectric is 2. So yeah, this will be 1/2 2C times 1/2 V squared. Right? So this comes out to be 1/2 CV squared. So yeah, our energy is cut in half. Now, there's less energy in the system, which means negative work was done. We don't have to force the dielectric in. If we get the dielectric close, it will be pulled into the capacitor because it's going to drop the energy. So instead of us having to apply a force, it's going to apply a force to the dielectric and pull it in to reduce the total amount of energy. That should be weird. Now we're out of time, but what you really, everything the same. 10 volt. This time, take my 2 capacitors, place them in parallel. Sure. We're going to go back to version 1 now. Still. And still. This one should be a little easier to do. Actually, no, I think it's about the same. So we close the switch, find out the energy of the system in the current state. We're going to insert the capacitor, find out the energy in the next state. This is what I get. Is this what you get? Yes, sir. Well, it's because I said it's what I get. I mean, it's the right answer. That's an increase of 100 microjoules. So in which case would it be harder to put the dielectric between the capacitor plates? It's got to be this one. Dylan only took 16 microjoules. This one takes 100 microjoules to do it, which means that the force required would have to be greater for the same size capacitors. Now, so far, not so terrible. And again, I think you could figure out what the charge is on each capacitor and how it changed. Of course, this one, charge on this capacitor probably wouldn't change. That's the Q. I think this one wouldn't change. It's got the same potential difference. Its value didn't change, but this one would have. It would double. But here's what I want you to think about. We've kept these connected to the potential difference the whole time, which means we've maintained a potential difference the whole time. But in this problem, I close the switch, charge it all up, open the switch, and now try to put the dielectric here. There is a complete pathway from one capacitor to the other. This one's a little bit harder to do.